Okay, we've got a worked example here, kinematics worked example for projectiles, and it's basically a particle being projected off what looks like it might be sort of the top of a cliff out into sea maybe, or out over land. Let's have a look. In this question, the unit vectors I and j are in a vertical plane, I being horizontal and j being vertical. So this is kind of quite normal. So basically it's being presented as a vector problem. In fact, all projectiles problems are essentially vector problems because they describe motion in 2 dimensions. Okay, so but we're just using sort of vector nomenclature here. All right, so let's go and have a look. Particle P is projected from the point A, which has position vector 47.5 j meters with respect to a fixed origin O. So that's there. Looks like it's say 47.5 meters, top of a cliff or up a building or something like that. The velocity of projection of P is 2ui plus 5uj meters per second. So we don't know the actual value in numeric terms, but looking at this, it looks like it's kind of it's more up than it is out. So we can say that much at the moment. The particle moves freely under gravity, passing through the point B with position vector 30i, as shown in the diagram, 30i meters. So that's that distance there. Okay, and show that the time taken for P to move from A to B is 5 seconds. All right, so this is a sort of fairly typical pattern in these projectile questions, where what we're actually looking to do is to calculate the time of travel by considering the vertical motion. Because in a vertical sense, if one was to look sort of straight on at the cliff, you'd see the particle passing up and down. Wouldn't really have a perspective of it coming out to sea or wherever. So we calculate the value of time of travel from the upward, and then we use that time of travel to either calculate the horizontal distance if we know the velocity, or calculate the velocity if we know the distance, which is the case here. We don't know the velocity, we don't know what u is, but we do know what the distance is. Okay, so what we do first of all is let's have a look in the vertical direction. So this is a little bit of notation here just to indicate that that's what I'm considering. And this is our Suvat equation, S equals ut plus half at squared, but of course u has been hijacked in my terms for this here, so it could be misleading if we just plant it into our Suvat equation. So I've used the v0 so as for the initial velocity. Now what I've got to remember, of course, is our frame of reference. So upwards and right are positive. So when we're looking at our displacement, of course, if the particle goes from A down to B, that is negative displacement. So that's why we've got minus 47.5. We've got the initial velocity 5u at the time, minus a half. Well, the acceleration, of course, is the same. Acceleration due to gravity is downwards, but our frame of reference is upwards. So then we have to consider minus g. So we've got minus a half g t squared. Okay, so that's sort of the first equation. Now we can't really solve this because for t, because we've got this u in here. So let's have a think about the horizontal now, and we're using this Suvat equation. Distance equals initial velocity times time. The initial velocity, of course, when velocity is constant in the rightward direction anyway, but we're just referring to it as the initial velocity. So substituting those in, and this time 30 is positive, equals 2ut. Now that gives us, with a bit of rearrangement, 5ut equals 75. And the reason for doing that is simply we've got 5u here, so we can just substitute that and eliminate u from our equation. So if we do that, we get this as a 75 instead, and rearrange that. We get this. and this, and if we take G to be 9.8, which is the kind of the standard or maybe default figure, then actually it works out that T squared is 25 and T equals 5. Again, arguably there's a solution to this equation, which is T equals -5. I think in the context of this problem, negative time is, we can discard. There are some problems where we may wish to consider negative time. T equals 0 is only really a reference point in time anyway. But I think in this one, I think we're quite entitled to discard T equals -5. So we've got T equals 5. And then if we go back to some, well, one of our equations, and obviously this is going to be the easiest one, that is going to give us a value of u equals 3. So well, we've done both these two parts A and B. So we've shown that the time for travel is 5 seconds and the value of u is 3. Now the final part is find the speed of P at B. Now the speed is a scalar. It's basically it's what's, how fast is it coming in this direction here at the point it actually hits the ground, or the sea, whatever. Now always with these things, basically, if we want to find the scalar, or certainly the speed, then what we need to do is need to find out the vector. So the vector velocity would be given, not just like the initial velocity really, but be given in 2 dimensions. There would be a rightward and an upward. Obviously, the upwards are going to be negative. The upwards are going to be negative, isn't it, because it's coming down. Okay, so and then from that vector, then we would go away and calculate the actual scalar value by using Pythagoras. So if we're looking at the equation v equals u plus at, now v, now this is the first time we've really written it as a vector. So u given is that. Now I've written this as a column vector, and I find it much easier to work with column vectors. And so I suggest you might try to kind of do that yourself, rather than writing it all on one line with i's and j's, which can get a bit more confusing and difficult to work with. So yeah, the column vectors form is nice, but if the question is asked in IJ form and they're asking you for a vector solution, then you would need to give that answer in the same terms as it's been asked. Okay, so v equals u plus at, v equals u plus, this is the acceleration. So there's no acceleration in the rightward direction, and the acceleration in the upward direction is minus g times the time, which is 5. Okay, so if we kind of just work that through, then this is what we get. We substitute our u equals 3 in there. We get this, and then what we have to do is just apply Pythagoras. So if it's 6 across and minus 10.1 down, draw a little triangle that has got those as the sides and work out what the hypotenuse is, and that gives us this answer. The v modulus v, this indicates the sort of the magnitude of the vector, which is the speed, 108.01, and we're talking about we're actually talking about meters per second. Just delete that out of there, but it's actually in meters per second. So 108.1 meters per second. So that is the solution to part C. So good. Well, I hope that's been useful, and I'll see you next time.